In second order or quadratical systems, the value of Q determines the distance between the pair of conjugate poles. For extremely large Q or extremely small Q, we can usually use kind of approximation to simplify the analysis. So first, let's consider what if we have a small Q, right, low Q approximation. Suppose we have a quadratical system, right? GS equals to 1 over 1 plus. So here we use the standard format, S over Q omega 0. For this denominator, right? So we can equal the denominator to 0. We can solve the poles of this system, right? But the poles really depends on value of Q. So for small Q, for Q smaller or equal to 0.5, this would have 2 real roots. Meaning that there be a pair of 2 real poles for this transfer function. And we can solve the value of the 2 roots. One is omega 1, just by equal the denominator to 0, right? Omega 1 equals to omega 0 over Q times 1 minus square root 1 minus 4Q squared divided by 2. And omega 2 equals to omega 0 over Q times 1 plus 1 minus 4Q squared square root or divided by 2. And we can introduce a quantity as FQ to represent this part so that we can simplify the expression for omega 1 and omega 2. So if we define FQ equals to 1 over 2, 1 plus, then we'll see that this omega 2 will right equal to omega 0 over Q times FQ. And for omega 1, this part can also be equal to 1 over FQ. So this will be Q over FQ. Actually, this part is equals to Q squared over FQ, right? So then this would be Q omega 0 over FQ. So the Q1, Q2 can be much simplified. And next, we take a look at this FQ value. How would FQ change with the change of Q? So we can plot the FQ's plot. So the x-axis is Q, y-axis is FQ. Since we are only considering the Q smaller than 0.5, right? So we only plot the shape of FQ to the left. So you will see that this would have such a kind of shape, right? Such kind of shape. Here, if Q equals to 0.5, right? So FQ will be equals to 0.5. And if Q equals to 0, this will be equals to 1, right? And with the decrease of Q, the FQ will increase. So we mark one special point like here. Suppose here is 0.3. If Q equals 0.3, you can calculate this number will be very close to 1. They're very close to 1. Okay, so generally, if Q is much smaller than 0.5, so for Q much smaller than 1/2, we can approximately equal FQ to be 1. So this can save us a lot of energy to calculate, right? To calculate. So if this assumption is valid, then we can see that omega 1, right? Omega 1 would be roughly equal to Q omega 0 because FQ is 1. Equals to Q times omega 0. And we have the expression for Q and omega 0, right? So Q is like R times C over L. And omega 0 is the resonance frequency, right? Between L and C. So combining them together, this would be equals to R over L. And omega 2 would approximately equals to omega 0 over Q. The fraction of omega 0 and Q, right? So here is the 1 over square root LC times 1 over R times L over C. This equals to 1 over RC. Now let's look at the result here, right? This is like kind of the pole introduced from the R resistor and the inductor, right? RL impact. And here is exactly the RC impact, right? RC is the time constant. So it's like we have, if Q is much smaller than 0.5, then it's like we have two separate poles, right? Two separate real poles. One pole is determined by the effect of R and L. One is determined by the effect of RC. And we can plot the magnitude plot accordingly. So it would be like this. Initially, it's 0 dB. At the omega 1, right? Omega 1 equals to Q omega 0. So there will be minus 20 dB per decade. And here is omega 2, which is omega 0 over Q. Another pole, which incur additional minus 20 dB per decade. So overall, it's minus 40 dB per decade. Because Q is much smaller than 0.5, so these 2 points are far away, right? So it's like two individual poles take effect separately. Okay, that is for low Q approximation. Next, let's look at the high Q approximation. For high Q approximation, we can consider a specific circuit example. Like we have a input source here as V1S. And we have a RLC network. But this time, the capacitor has a equivalent series resistance. CL. And here is the load resistance, and here is output voltage. So this is like the case of the output stage for buck converter, considering the ESR of the filtering capacitor, right? So for such a specific circuit, we have kind of intuition. The intuition tells us, can we decompose this complicated circuit into two separate, relatively simple circuits? So let's try to do this. So we can equivalent this circuit into two sub-circuits. The first one, we do not consider RC. Suppose RC doesn't exist. So here's the LC R. Input voltage, output voltage. And the second sub-circuit, we consider this RC, but ignore the effect of the R. So V1S, ESR, C. We leave it open here, right? So here is short, here is open. So those two sub-circuits is like we consider each damping component separately. We first consider R here, and then consider RC here. And for this sub-circuit, we can calculate its transfer function. GS equals to, so basically it's a quadratic pole response, right? 1 over 1 plus S over Q load. Because we only consider load resistor, we mark this Q as Q load. Omega 0 plus S over omega 0 squared. And for this sub-circuit, we only consider RC. Right? We can calculate its transfer function, which is also a quadratic pole response, but with a 0. 1 over S over omega 0. There is a left half plane 0 combined with a quadratic pole response. Here we introduce another Q as QC. QC means the quality factor incurred by the RC in this circuit. So for those two expressions, we can write the expression for Q load. Remember, right? Q load, right, equals to R over R0. So where R0 is the characteristics impedance equals to square root L over C. And basically, it agrees with the definition, right? The peak energy stored energy over the peak, the dissipated energy per cycle. And omega 0 equals to the resonant frequency between L and C. And QC, right? QC equals to RC divided by RO. Right? Divided by RO. Okay, so that is the intuition tells us. Next, let's look at the accurate analysis for this complete circuit. So based on this circuit, we can also derive the expression for its transfer function. So basically, we would have G S equals to 1 plus S RC times capacitance divided by 1 plus S times L over R plus RC C plus S squared LC 1 plus RC over R. Now let's see whether our intuition is correct or not. Right? We look at this one, this transfer function. We can also try to express it in standard format. We can normalize it. GS would be equal to 1 plus. Here would be the 0, right? 0 frequency, 1 over S over omega 0. So where omega 0 equals to 1 over RC times C. Okay. And denominator can also be normalized by those quantities Q load, omega 0, and QC, right? So this can be represented by 1 plus. Okay, so what S over omega 0 times this can be represented by the Q load and QC, right? Q load and QC. So basically this happens to be 1 over Q load plus 1 over QC. And then we consider the second order term, right? S squared over omega 0 square. We put the square outside the bracket times 1 plus 1 over the product of Q load and QC. That is the normalized expression for the system transfer function. Now let's consider the high Q approximation, right? For high Q approximation means that if Q load much larger than 1 and the QC also very large, much larger than 1. So basically, if you look at those two expressions, they means that the characteristics impedance is very low, right? And so that R is much larger than R0, or RC is also larger than R0. If two assumptions are valid, look at here. This is the product of two large number. Then we invert it. So this can be roughly equals to 0, ignored, right? So then we would have the GS simplified. And also we look at here. This is indeed the parallel effect of 2Q, right? Consider if you have two resistors in parallel, you will have the equivalent resistance in this format. So here this is like we have 2Q in parallel, So we can denote this GS in simplified result as 1 plus S over Q, S over omega 0 times Q load parallel with QC. S over omega 0 square. 1 over Q load in parallel with QC plus S over omega 0 square. So what does this mean, right? It means that for high Q cases, this system is like we have, this system contains two damping components, RC and R. If Q is large, right? If Q is large for those two damping cases, the system's behavior is like we have a unified Q, right? Unified Q. The unified Q will have a equivalent quality factor, right? So we call this as composite quality factor. So which is approximately equal to Q load. So this quality factor in parallel with this resistor incurred quality factor equals to 1 over Q load plus 1 over QC. So this assumption will make our analysis much simplified. Okay, now let's erase the whiteboard. Okay, we have erased the blackboard. Now let's do the kind of accurate analysis. So basically, this equation is the accurate result, right? So if you look at the circuit itself, this circuit contains two damping factors, damping factor RC and damping factor R, right? So essentially, those two damping factors, Q load and QC, they affect together, right? Both two damping terms, Q load and QC, they work together to affect both the corner frequency and the composite Q factor. Corner frequency in the magnitude plot, right? And the Q factor. So now let's normalize this accurate result by its effective corner frequency and effective Q factor. So we introduce QE as effective quality factor and omega E as effective corner frequency. Then we will have the GS equals to 1 plus S over omega Z divided by 1 plus S over omega E, the effective corner frequency, times 1 over effective quality factor of the entire system plus S over omega E square. If you compare here and here, right, without the approximation, you can easily write the expression for omega e. Omega e equals to omega 0 divided by FH Q load QC product. FH is a function we introduced here. So where FH equals to square root, right? Square root of this quantity. 1 plus 1 over Q load QC. And also we can, by mapping here to here, we can also write the expression of the effective quality factor. So QE would be equal to Q load parallel with QC times FH Q load times QC. So that is the accurate analysis without kind of approximation here. Now let's see how accurate is our previous approximation, right? So basically we can plot this function, right? Plot this function to see how much accuracy do we have. So let's plot this function. So the x-axis is the product of Q load and QC. Y-axis is FH. This is very simple to plot, right? You can use MATLAB to plot it. Here I just gave you an initial idea about how will it change. So basically with the increase of this Q product, this will decrease, right? So basically here is 1 unit, because if the product approach infinity, the FH will approach to 1. So 1 is the boundary. And but if, for example, if Q product is small, like 0.5, you can also see, right? 0.5 here is square root 3, right? So here is like 1.732. And for example, if here is 5, 1.2 square root, right? 1.2 square root is roughly like 1.1. 1.1. This tells you how it changes. So for such a profile, we can see that if the product of Q load and QC is bigger than 5, then we would have the FH smaller than 1.1, right? So the assumption that 1.1 is roughly equal to 1 is relatively accurate, right? So if we consider FH is approximately equal to 1, then you will see that, right? This would approximately equals to omega 0, right? And Q will approximately equals to the parallel of those two Qs. This kind of validate the accuracy of the previous approximation. Okay. So in summary, when Q is very small, the quadratic system is like we have two separate real poles. But when Q is very, very large, in a resonant circuit with two damping components, like two resistors, we would have a composite Q. This composite Q is equivalent to the parallel of two separate Qs. This approximation can help us to much simplify the circuit analysis process.